Hello friends, welcome to my lecture on solution of first order nonlinear equations. So this is our first lecture on the how to find the solution of nonlinear equations that are of first degree but not of that are of first order but not of first degree. So let us see. We have so far discussed how to determine the solution of Lagrange linear partial differential equation, which is of the form P into P plus Q into Q equal to R, where P, Q and R, as you know, they are functions of x by z. And so this is a first order and first degree linear partial differential equation, partial differential equation which is linear in P and Q. Now we shall be considering first order partial differential equations which are not of first degree. So if they are not of first degree, then they will be nonlinear partial differential equations. So let us see how we solve first order nonlinear partial differential equations. And such solution of nonlinear partial differential equations present considerable difficulties. First we will focus on before giving the general method, that is the Charpit method of solving such equations, we shall present some special types of equations whose solutions can be easily determined. So many equations we shall see can be reduced to few standard forms and therefore can be solved generally by methods which are shorter than Charpit method. So let us first discuss the equations of the form f p q equal to 0. Such partial differential equations where the partial derivatives p and q, that is delta z by delta x and delta z by delta y occur, and they do not involve the variables x, y and z. They consider they come under this category of equations of the form f p q equal to 0. So in the case of these equations f p q equal to 0, we see that the complete integral is given by z equal to ax plus by plus c. Now I want to remind you that the complete integral is defined as the solution of the differential equation which contains as many arbitrary constants as there are independent variables in the differential equation. So there are two independent variables here, x and y. So this is a solution of the partial differential equation f p q equal to 0, because here a and b are connected by the relation f a b equal to 0. If you find the partial derivatives of this equation z equal to ax plus by plus c with respect to x and y, then what we get is the derivative of z with respect to x, which is p, we have denoted by p, comes out to be a, and the derivative of z with respect to y, which we have denoted by q, comes out to be b. Which when substituted in equation 2, that is f a b equal to 0, give us f p q equal to 0. So z equal to ax plus by plus c is a solution of f p q equal to 0, and moreover it involves two arbitrary constants, they are a and c. B is not an arbitrary constant, b is connected to a by the relation f a b equal to 0, so b can be said is as a function of a. So there are two arbitrary constants a and c, and because of these two arbitrary constants, and this is a solution of the equation f p q equal to 0 which contains two independent variables, it can be called as the complete integral of f p q equal to 0. Now now if you remember, from the complete integral one can determine the general solution. If the complete integral is given by f x by z a b equal to 0, where a and b are arbitrary constants, then to determine the general integral, what we do is, let us say let b be an arbitrary function of a where phi is arbitrary, so then we have the equation 1, then we have from 1 f x by z a phi a equal to 0. Now by eliminating a, the arbitrary constant a, between the equations fx by z a phi a equal to 0 and the partial derivative of f with respect to a equal to 0. Between these two equations we obtain the general integral of the partial differential equation of first order. Differential equation of f x by z p equal to 0. So this we have known already. Okay. So in order to find the general solution from the complete integral, okay, the complete integral is z equal to ax plus by plus c. Okay. Fab equal to 0 gives you since Fab is equal to 0, we can say we may take b as a function of a, b as a function of a, and the arbitrary constant c, and c is equal to phi a, where phi is an arbitrary function. So then z will be equal to ax plus h by a, h a into by plus phi a. Okay. So that we have the equation ax plus h a into by minus z plus phi a equal to 0. Thus we have this equation. So this equation is same as the equation fx by z, a phi a equal to 0. We differentiate it with respect to a. So differentiating it, we get x plus h dash a into y plus phi dash a equal to 0. So we then, on eliminating a between this equation, let me call it as 1 and this as 2. So when we eliminate a, on eliminating a between 1 and 2, we get the general solution. The general integral. So this is how we will obtain the general integral from the complete integral. We have already said that a partial differential equation is said to be completely solved if we get the complete integral, general integral, and the singular solution of the partial differential equation. So we have obtained the complete integral. General integral we can obtain from here, and let us now discuss how we can obtain the complete integral. Now if you, so now how to obtain the singular integral? To obtain the singular integral from the complete integral, let us recall that if the complete integral is f(x) by z ab equal to 0 of the if the complete integral is this of the partial differential equation f(x) by z pq equal to 0, then the complete integral is obtained, then the singular integral is obtained by eliminating a and b between the equations f(x) by z ab equal to 0, delta f over delta a equal to 0 and delta f over delta v equal to 0. Okay. So, by eliminating the two arbitrary constants a and b from these three equations, we arrive at the singular integral. Now, in this case what happens is, let us look at the complete integral. The complete integral is z equal to, so here the complete integral is z equal to a plus ax plus by, b is equal to ha, so h into a into by plus c. So, there are two arbitrary constants a and c. We can write it in the form f(x) by z ab equal to 0. So, r z minus ax minus ha into by minus c equal to 0. So, this equation is of the form f(x) by z a b equal to 0. Here the arbitrary constants are a and c. Now, let us differentiate this with respect to a. So, differentiating with respect to a, we have, okay, so minus x minus h dash a into by equal to 0. And when we differentiate this with respect to c, next differentiating with respect to the other arbitrary constant c, we find minus 1 equal to 0. So, we have to now eliminate the two arbitrary constants a and c between this equation and this equation. Now, minus 1 equal to 0 is not possible. So, therefore, there is no singular integral in this case. So, in this case of the partial differential equation, we have only complete integral and general integral. Now, let us go to the example 1, pq plus p plus q equal to 0. So, let us consider pq plus p plus q equal to 0. Now, you can see that this differential equation is a non-linear differential equation, because the partial derivatives p and q, they occur as a product in the first term. So, it is a first order differential equation, but it is not linear in p and q. Now, so it, and moreover there only here p and q occur, x by z do not occur. So, it is of the type 1, it is a partial differential equation of type 1. So its complete integral could be written as z equal to ax plus by plus c, where if I write it as fpq equal to pq plus p plus q, then here fab equal to 0. So fab equal to 0, or you can say ab plus a plus b equal to 0. So from here I can get the value of b equal to minus a upon a plus 1, and hence the complete integral is z equal to ax minus a over a plus 1 into y plus c. From the complete integral we can obtain the general integral. So to obtain the general integral, let us take c to be some arbitrary function of a, where phi is arbitrary. Where phi is arbitrary. Now then we can say then 1 can be written as ax minus z minus a over a plus 1 into y plus phi a equal to 0. And differentiating this with respect to a, we have x minus, now a over a plus 1 is nothing but 1 minus 1 upon a plus 1. So when you differentiate a over a plus 1 with respect to a, what you get is d over dA of a over a plus 1. This gives you 1 over a plus 1 whole square. So here we shall have minus 1 upon a plus 1 whole square into y plus phi dash a equal to 0. So let me call it as equation number 1, and this is equation number 2. Eliminating a between 1 and 2, we obtain the general integral. Okay, now to obtain the singular integral, as we did said earlier, a and c are two arbitrary constants in this complete integral. So we shall differentiate it partially with respect to a and with respect to c, and when we differentiate this equation with respect to c, what we will have is 1 equal to 0. If we write it as ax minus a over a plus 1 by plus c minus z equal to 0, and then differentiated with respect to c, we obtain 1 equal to 0, and 1 equal to 0 is not possible. So the singular solution or singular integral does not exist. Again I repeat, but we have the complete integral z equal to ax minus a over a plus 1 by plus c. So you can write it as ax minus a over a plus 1 by plus c minus z equal to 0. then we have to differentiate partially with respect to A and with respect to C. When we differentiate it with respect to C, we get 1 equal to 0, which is not possible, and so the singular solution does not exist in this case. Now let us go over to next question, where we will see that by suitable substitutions we shall be able to bring this differential equation, partial differential equation of first order, which is non-linear, to the form f p q equal to 0. So let us analyze this equation closely. We have x square p square plus y square q square equal to z square. Let us divide this equation by z square, assuming that z is not equal to 0. So we have x p over z whole square plus by q divided by z whole square equal to 1 if z is not 0. Okay, now this is what? X over z, p is delta z by delta x plus this is by over z we can write like this. Now this can also be expressed as r 1 over z delta z divided by 1 by x delta x whole square plus 1 by z So let us define capital X equal to small capital X equal to ln small x, capital Y equal to ln small y, and capital Z equal to ln small z, this small z. So then dx over x dx will be 1 over x, dy over dy will be 1 by y, and dz over dz, this is capital Z, this is big Z, equal to 1 by z. And so this can be written as delta ln z, I can write like this, delta ln x whole square plus delta ln z over delta ln y whole square equal to 1, or we can say delta z over delta x whole square plus delta z over delta y whole square equal to 1. Now this is of the type, this equation is of the type 1. So its complete integral is z equal to ax plus by plus c. Let me write small c, ax plus by plus c, where we have so where if delta z over delta x, this is a, so then b square is equal to 1 minus a square, so where b is equal to plus minus under root 1 minus a square. So thus we have this is ln z and then a times ln x plus minus under root 1 minus a square into ln by, and this c we can write as ln c dash. let us write C as, where C is equal to ln C dash. So then we can write Z equal to x to the power a by to the power plus minus under root 1 minus a square into C dash. Let me write it as Z equal to C dash times x to the power a by to the power plus minus under root 1 minus a square, where a and C dash are two arbitrary constants. So this is complete integral of the given partial differential equation. Now what we will do is, to determine the general integral from this equation, we have to take C dash equal to phi into a. So to determine the general integral from the complementary integral from, let me call it equation 1, from 1 we let C dash equal to some arbitrary function of a, where phi is arbitrary. Okay, so we have phi a into x to the power a by to the power plus minus under root 1 minus a square. This is z, this is equal to z. Now we can make it simpler, okay, by taking, say, a equal to, suppose a equal to cos alpha, okay, a is equal to cos alpha, then we shall have z equal to phi of cos alpha. So I can write it as some psi alpha, okay, where psi alpha is phi of cos alpha, x to the power cos alpha and then by to the power plus minus psi alpha, where psi alpha is phi of cos alpha. Now we differentiate this equation with respect to alpha, okay. So we shall have or we can say psi alpha minus x to the power cos alpha, psi alpha into x to the power cos alpha by to the power plus minus sin alpha minus z equal to 0. So what we will do is, let me call it as equation number 2, okay, and then we differentiate this with respect to alpha. So psi dash alpha into x to the power cos alpha by to the power plus minus sin alpha plus psi alpha x to the power be different cos alpha when we differentiate x to the power cos alpha with respect to alpha, what we get is x to the power cos alpha and then x to the power a if we differentiate with respect to a to the power x, if we differentiate with respect to x we get a to the power x log a. So x to the power this we differentiate minus sin alpha and then we get x to the power alpha, we are differentiating with respect to alpha. So x to the power cos alpha into minus sin alpha into ln x we shall have by to the power plus minus sin alpha and then psi alpha x to the power cos alpha by to the power plus minus sin alpha into plus minus cos alpha ln by minus equal to 0. So this is our equation number, let me call it equation number 3. So by eliminating alpha between equation number 2 or this equation and 3, we get the general integral. So general integral is obtained the singular integral is obtained by eliminating a and c dash, or you can say by eliminating by eliminating a and c dash between equation 1 and then its partial differentiation with respect to a and c dash will give you two more equations. So by eliminating a and c dash, so by differentiating equation 1 with respect to a and c dash, we will have two more equations. We'll have two more equations. We'll have two equations. If we take it as if we write f x by z a c dash equal to z minus c dash times x to the power a by to the power plus minus under root 1 minus a square, then equal to 0, then delta f by delta a equal to 0 and delta f by delta c equal to 0. Okay. So if we write f x y z a c dash to be equal to this, then by differentiating this with respect to a and with respect to c dash, we shall have these two equations. So eliminating a and c dash between these three equations, we shall see that three equations. I can call them as say 4, 5, 6. Four to 6, we shall obtain z equal to 0. Z equal to 0 is therefore the singular integral. So in this case, z equal to 0 is the singular integral. We can see that z equal to 0 satisfies this equation x square p square plus y square q square equal to z square, because z equal to 0 means p and q both are zeros, so both sides are 0 0. So let us take third question where we have x plus y times p plus q whole square and then x minus y p minus q whole square. So we shall make certain some suitable substitution and will reduce it to the form which we have considered in type 1. So let us say let us define x equal to root x plus y and y equal to root x minus y. Let us define capital X equal to this and capital Y equal to this. Then delta x over delta x is 1 over 2 root x plus y. Delta x over delta y is 1 over 2 root x plus y, and here when we differentiate y with respect to x partially, we get 1 over 2 root x minus y, and here we get delta y over delta y as minus 1 over 2 root x minus y. Now P is delta z over delta x. We can write it as delta z over delta x into delta x by delta x plus delta z over delta y into delta y over delta x, because capital X, capital Y both are functions of x. So we have here delta x over delta x is 1 over 2 root x plus y is 1 over 2x. So 1 over 2x, and then delta z y over delta x, delta y over delta x 1 over 2 root x minus y, and 1 over 2 dot x minus y is 1 over 2y. This is 1 over 2x. So we have 1 over 2y, and similarly q, which is delta z by delta y, it can be written as this, okay, and this is equal to delta x over delta y, this is 1 over 2x, and delta y over delta y is minus 1 over 2y. So we will have 1 over okay. Now let us add the equations 1 and 2. So adding 1 and 2, we get P plus Q equal to one over 2x delta z by delta x, we get 1 over x and P minus Q similarly, and subtracting two from 1, we get P minus Q equal to 1 over by delta z over delta y. Okay, now so we will put the values here. So x plus y is x square. So thus the given equation becomes partial differential equation reduces to we have x square into P plus Q whole square. So 1 over x square delta z by delta x square plus x minus y is y square into P minus Q whole square. So 1 over y square this equal to 1. So here we have x square. So this cancel with this and this cancels with this, and we have which is a partial differential equation of the form 1, where z is the dependent variable, capital X, capital Y are the independent variables. So it is of type 1. So the complete integral is z equal to ax plus minus under root 1 minus a square, this is capital X here, capital Y plus some constant, let us say c. Let us put the value of capital X. So a times square root x plus y plus minus under root 1 minus a square, then y is square root x minus y plus c. So z equal to a times square root x plus by plus minus square root 1 minus a square x minus by plus c. This is a square plus b square equal to 1, so b is plus minus under root 1 minus a square, which we have put here. So this is the complete integral. Now from the complete integral, as we have seen on the earlier examples, we will for the general integral we will write c as phi a and then differentiate the equation with respect to a and then eliminate a between this equation where c is replaced by phi a and its derived equation where we differentiate this equation with respect to a partially, and then in order to find the, and then we eliminate a, so we to get the general integral, and when we want to find the singular integral we will eliminate the two arbitrary constants a and c between this equation and its derived equations, which are the partial derivatives of this equation with respect to a and c. So by eliminating a and c between this equation and those equations, we can obtain the singular integral. So that the usual that is means by the usual method of obtaining the singular integral we can do this. So once we have the complete integral, we can obtain the general integral and the singular integral for the given partial differential equations. So this is how we solve the problems which occur in the case f p q equal to 0, that is of type 1, where the differential equation only contains the partial derivatives p and q, the variables x, y, z do not occur. With that I would like to conclude my lecture. Thank you very much for your attention.